In the second part, discussion, or chapter 3 on Bernoulli equation, we'll look at the definition of pressures, various pressures, look at the application of the Bernoulli equation to flow through various measurement devices such as weirs, orifices, and Venturi meters. So we'll show how practical the equation actually is. So here we'll define static and stagnation pressures. We've already talked about static pressures in the second chapter, but it will be good here to provide some context for static pressure and stagnation pressures so you can see what the differences are. Let's consider here we have fluid flow occurring in this pipe that's shown in the lower part of this diagram. The velocity is uniform. Remember, we do not have any shear stresses occurring, so the velocity will be uniform across the cross-section in this case. We have various points in the fluid, 1, 2, 3, 4, that are defined, and various pressures that are defined. Okay, a small interruption there. Alright, so we've got water, or we've got a fluid flowing in this pipe, and we've got a manometer sticking out of the top on the left-hand side, that left-hand tube, and then what's called a Pitot tube, which is the tube on the right-hand side. The water, or the fluid, is standing in the left-hand tube to a height of h above 0.1. That is, the distance between 0.1 and 0.4 is equal to h. The height above the elevation of the tube is h subscript 4-3. And then for the Pitot tube, the water height is equal to capital H, and that's the distance between 0.2 and the top of the liquid surface inside that tube. That's on the right hand side. At point 1, the velocity is equal to v, that is, the velocity at point 1 is equal to v, which is the uniform velocity in the tube, and at point 2, which is just at the opening to the Pitot tube, the velocity is equal to 0. This will be defined later, but the velocity, or the point 2, is what's called the stagnation point. It's the point at which the velocity goes to 0 as a result of the fluid meeting up with an object. And we'll look at some different types of objects as to cases where we have stagnation points. The pressure at point 2 is equal to, the pressure head at point 2 is capital H, so the pressure is just capital H multiplied by the density, the unit weight of the fluid, and that's just equal to P2, and P2 is equal to P1 plus 1/2 rho V1 squared. Now in here, in that sum, the 1/2 rho V squared is what's called the stagnation pressure. P1 here is just the is the hydrostatic pressure, which is just gamma times H. Some examples of stagnation pressure are shown here. Like for instance, a baseball that's been thrown, it's moving at a certain velocity. Streamlines pass around that baseball, and at the point where a streamline meets the baseball head-on, perpendicular to it, at that point is a stagnation point. There's no velocity at that point. On the right hand side, another stagnation point would be where water is being sprayed on a surface, like on a car, as in this example. And when the spray hits the surface, right at that point the fluid has zero velocity, and that's called a stagnation point. So when the fluid drops from the velocity v to 0, the stagnation pressure is 1/2 rho v squared. So we have P stagnation pressure is equal to 1/2 rho v squared, where v would be the free stream velocity upstream of the stagnation point. All right, so Pitot tube is Pitot, and here's an example of the Pitot tube shown here. It's like the one that we showed in the previous diagram, but here there's a little bit more detail to it. Here we've got the velocity v upstream, and the fluid pressure upstream is equal to P. That is the static pressure, hydrostatic pressure upstream of the point is equal to P. And the fluid comes to point 2, and of course is going to pass around point 2, but right at point 2 the velocity will be equal to 0, so you'll have a stagnation pressure at that point, which would be equal to 1/2 rho v squared. To calculate then the velocity, the purpose of a Pitot tube is to be able to calculate the velocity of the fluid. So what you can do is to take a tube like this, set it in a free stream velocity fluid, a free-flowing fluid. If you want to know what the velocity is, then you can measure the height at which the fluid will stand within this tube, and by knowing the hydrostatic pressure, you can calculate you can determine what the total pressure is, which would be the hydrostatic plus the stagnation pressure, and if you know the stagnation pressure, you can calculate the velocity. So in this diagram, the P3 is the stagnation pressure, P3 would be the pressure that's being measured is the stagnation pressure, and P4 is the hydrostatic pressure. Okay, if we go back to previous diagram, we can look at that and see how that relates to what we had before. And here in this diagram again, P2 associated with the height that the water rises inside the tube. That height, capital H, is related to both the static pressure and the stagnation pressure. This right here is the static pressure, and then of course the difference between capital H and P1 is just the stagnation pressure. Alright, so the Pitot tube is shown here. This would be for just showing the effect that there might be in accurately measuring the velocity. Now this is very important for measuring the velocity, let's say, of an airplane. So in flying an airplane, the pilot needs to know the velocity of the plane, because if the velocity slows too much, then the plane can stall, and of course if it stalls, it'll go out of control and can crash. So this Pitot tube that's shown here is an example of the type of Pitot tube that's used on an airplane. And on here, the points, openings in the tube that are measuring the static pressure are the ones I just circled at point 1. Those would be measuring the static pressure in the fluid. whereas the stagnation pressure or the stagnation point would occur at point 2, and you would be measuring the pressure associated with that. As we've already stated, that total pressure that's measured at point 2, subtracting off the static pressure that's measured here, or that's measured using those openings at point 1, will be the stagnation pressure, which of course again will be equal to 1/2 rho v squared. And so if you measure the total pressure, subtract off the static pressure that's measured using the openings at point 1, you can then calculate the quantity 1/2 rho v squared, and if you know the density of the fluid, you can calculate the velocity. Now, this diagram below is supposedly going to show us the kinds of errors that you can have in measuring the static pressure. Not the stagnation pressure, but the static pressure. So it's very important that the holes that are put in there not have any kind of imperfections. And P here is the actual static pressure, which we want to measure very accurately. And then the P1 would be the measured, what your sensor is telling you the hydrostatic pressure is at point 1. And what is illustrated here is that, you know, if you have a hole and it's got a little bit of a burr on it like this, well then the pressure P1 that you measure will actually be greater than the actual static pressure. If you have a burr right here, the fluid will be pushed upward like this, and that leads to a pressure P1 being less than the actual static pressure. And then here, this would be a properly designed or constructed tube where the pressure that you would measure would be equal to the actual pressure, which is, of course, as I mentioned before, is very important. If you inaccurately measure that static pressure, your measurement of the stagnation pressure will be off. And if your stagnation pressure is off, then your velocity you calculate will be incorrect. This can lead to big problems, for instance, when it comes to flying an airplane. This again just shows the construction, what it might look like for an airplane, the type of Pitot tube that's used for aircraft. So just the different parts of it are shown here. Okay, let's move on, and we'll look at the problem of fluid flowing out of a container. And here we're going to be examining the characteristics of what we call free jets. So let's say you have a container, and you'll see this in the laboratory experiment lab 2, where you have a container that's got a liquid in it, and you've got an opening in that container, and you open it up. You've got an opening that's, and you have a valve on it. Maybe open up that valve so that the fluid flows out. The fluid will come out as a jet, and that jet has certain characteristics, and that's what we're going to be examining here. Going to be showing how you can determine the characteristics of that flow and what the things that affect the characteristics of that flow. So let's look at this situation here. Make believe we've got a container or a reservoir that's got fluid standing in it. It's got an opening in the bottom of that container, and that opening is is open so that the fluid can pass out of it. It's at a water level is a height h above the opening itself. The opening has a diameter equal to d, and maybe there's a transition from the tank to the opening. The surface of that opening is curved. It could actually be let's say a right angle that it would take. In this case, it looks like it takes somewhat of a curved surface, but we'll be looking at different cases, and that does affect the character of the flow. the fluid will pass out of that opening at a velocity v. So we've got various points marked on here, point 1, point 2, point 3, and point 5. And let's just say that point 5 is at a height or distance h below the opening. On the right hand side, in a little bit more detail, we can see 2 points, point 2, which is the same as the point 2 on the left hand side, and then a point 4, which is right on the edge of the opening where it meets the surface of the container right at that point. And we've got streamlines marked out in each case. So let's say that we start off at point 1, and we're going to have a particle that's going to move from point 1 all the way along that streamline towards point 2. Bernoulli's equation says that the conditions at point 1 are P1 plus 1/2 rho V1 squared plus Z1 is equal to a constant C. Let's call it C1. Well, in here, the pressure at point 1, if we're using gauge pressure, the pressure at point 1 is equal to 0. This is atmospheric pressure. The elevation at point 1, if we use this point 2 as our datum, our reference point, Z1 will be equal to D. The height, or sorry, Z1 is equal to H. It's the height that the water surface is above the outlet. And then, of course, here the tank is considered to be very large relative to the size of the opening. So we can say here that V1, the velocity of the fluid at point 1, is approximately equal to 0. So if we take those three variables, we can say that C1, which is equal to P1 plus V1 squared over times rho divided by 2, plus Z1 is equal to a constant. That constant is going to be equal to H. That is, C1 is equal to H. Along that streamline between point 1 and point 2, that constant remains, or that the sum of those numbers remains a constant equal to H. So when we get to point 2, we're going to have P2 plus 1/2 rho V2 squared plus Z2 is going to be equal to H, equal to the constant that we just defined. Well, Z2 here at point 2 is equal to 0. The value of P2 here is just equal to atmospheric pressure, because the fluid on either side here of this jet is at atmospheric pressure. PA is equal to 0. So the pressure all the way across actually has to be, the water pressure inside that column has to be 0 all the way across. This may not be exactly the case if there were some curvature, if the jet were curved in any way, but in this case, because the streamlines are straight coming out of that jet, the water pressure is the same as the atmospheric pressure all the way around the jet, and that atmospheric pressure is 0, so the water pressure is 0 all the way across this line here. And so if Z2 is equal to 0, P2 is equal to 0, that means that 1/2 rho V2 squared is equal to H. And so we can solve for V2. When we do that, that's what this is. This is, we'll call this V2 right here. That's V2. If we solve for V2, we just get an equation, square root of 2GH. I do have to make one small correction here, and that is that this should have gamma multiplied by it up here. And so this should be gamma down here. Gamma multiplied times Z2. That's the only way you can end up with B2 to be equal to 2 times, or square root of 2GH. So you can go ahead and solve for that, is what it turns out to be. Gamma is just equal to rho times G, as you'll recall. Alright, so that's the general equation. V2 is equal to the square root of 2GH is the general equation for flow out of a jet. And we're going to modify that a bit because of the fact that the jet does not have parallel streamlines coming out as it exit the opening of the container. And so we'll do that in the next slides. Okay. So this comment that I make right here about the fact that the result shows then that the potential energy that the fluid has at point 1, there's no velocity at point 1, so there's no kinetic energy at point 1. It's all just potential energy, the elevation of the point. That the potential energy is completely converted to kinetic energy, going from point 1 to point 2. If we have the jet on the side of the container as shown here, we can see that again, if we make the assumption that the fluid does not have any curvature to the streamlines when it's coming out of the jet or coming out of the opening, then the fluid pressure across the jet will be uniform, and since the pressure on the outside of the jet is equal to PA, the pressure inside the fluid here will just be equal to the air pressure, or equal to 0. Because of the fact that the value of H that applies to any given streamline, if we're going from here to here, or if we're going from here to here, or if we're going from here to here, the value of H that we use in calculating the velocity changes. It'll be the smallest right here at point 1, it'll be the highest at point 3. So the velocity will be higher at point 3. In each case, the velocity will be equal to the square root of 2GH, and the H, as I mentioned, will be dependent on which point I'm starting from here. So that's why what we see is we see a higher velocity in the bottom of this jet than you see in the top of the jet. And what you see over here is the example of it in a laboratory setting, where you got a container that's got a hole in the side. The jet is coming out. It appears to be that the streamlines are probably parallel to each other and not converging in any way, but we will look at that in more detail. Generally, the thickness of the jet will be small to the relative to the height of the container, of the fluid in the container. So it's usually accurate enough just to use the height of the water surface above the center of the jet, in this case above point 2, to determine what the H is that you would use, and that's the value you would use in calculating the velocity. Now, in reality, what happens is that the streamlines are not straight coming out of the jet, and this slide shows that. So what we have, focusing on this jet, we've got a sharp edge opening, and what happens is that the streamlines have to pass around this corner, and because of the velocity as it approaches that corner, it requires a great deal of force to curve the streamline around that corner. It's not possible to get this streamline for here, for instance, to pass down and just come straight out like this, or this one here to come straight out like that. Instead, there's some acceleration that goes on, that the jet does curve, the surface does curve there, the streamline does curve, but it's not a right angle. It's impossible for it to turn a complete right angle at that point. So what we get is that the point outside the jet where the streamlines become parallel to each other again, or straight, is some distance away from the opening itself. And the actual diameter of the jet, as you see here, d sub j, will be smaller than the diameter of the opening. So the diameter opening here is dh, the diameter of the jet is dj, and dj will always be smaller than the value of dh. What this does then is it changes the cross-sectional area of the flow such that we need to have a correction to, in order to be able to calculate the discharge of the jet coming out of the jet, we need to have a correction factor. It's called a contraction coefficient. That contraction coefficient is just the ratio of the area of the actual jet based on d sub j to the area of the opening based on the size of the opening, d sub h. The velocity at the outlet is still equal to the quantity that we had before. D is equal to square root of 2gh, but the discharge will be equal to the velocity times the area of the jet, and that area of the jet is corrected now for this convergence of the streamlines that make the area of the jet smaller than the area of the actual opening. So what we usually measure is the area of the opening. We usually don't necessarily know what the area or the diameter of the jet is ahead of time. So in order to calculate the discharge in practical terms, we use this correction factor to correct the area for the area of the jet, and it turns out to be that we multiply C sub c times the actual area of the opening times the square root of 2gh. And what we can do is we can look it up in a reference book as to what that contraction coefficient is. So there's some various values of that contraction coefficient, and that's shown here. Textbook has other ones, but in engineering practice we can look these numbers up to figure out what would be appropriate value to use in a particular design. So for this knife-edged exit or opening that you see in the figure A, the contraction coefficient is 0.61. In the case of this nice rounded edge that you see in B, the streamlines are able to make it around the corner such that by the time they reach the exit of the opening right here, the streamlines are parallel to each other, and there's no contraction at all, such that now the contraction coefficient is equal to 1. The area of the jet is just basically equal to the area of the opening. For this sharp edge exit, the contraction coefficient is the same as the one in A, which is 0.61. And then for this one right here, the conditions are even worse than they were in either A or C as far as the contraction of the streamlines and the contraction of the jet. And so here the contraction coefficient is equal to 0.5.